Algorithms. Let's try to understand what is an algorithm. It is a step-by-step approach to solve a particular problem. If there is a problem, what is the things that you are going to take care of? So the solution that you give should be crisp, right? It should be exactly what is required, right? If a problem is about swapping two numbers, you should be able to swap two numbers and with the most efficient approach. And when you define an algorithm or when you're writing an algorithm, it should be understood by a non-technical person, right? There should be no such language dependency in your algorithm, right? So this is what an algorithm is, a step-by-step approach to solve a particular problem. Your problem can be complex or it can be an easy problem. It is free from programming language. There are multiple possible algorithms to solve a given problem. Let's suppose I told you to swap two numbers, right? Now, one algorithm is wherein you can go ahead and create one temporary variable and then swap them. The another approach is that you're going to use addition and subtraction operators to solve the same. You're going to use these operators and you can solve this problem of swapping two numbers, right? Which one do you think is the efficient approach? Obviously, here you're using an extra variable and here you're not using any extra variable. So this seems to be a better approach. And obviously, it should be understood by a non-technical person. You should not be using language dependency code, like you should not use any language agnostic code, right? So it should be language independent. So let's see what is an algorithm analysis. This is again a step-by-step approach to solve a particular problem. It helps us identify which algorithm is optimal. Okay, this is the analysis part of algorithm, right? Herein, let's suppose I told you to swap. It helps us to understand the trade-off between time and space complexity, right? So there should be always, you should be able to understand the difference between time complexity and space complexity. And depending on that, you should be able to do a trade-off as well. Now, when I mean trade-off, you should be able to depict that are you going to keep your time complexity efficient, or are you going to use your time efficiently, or are you going to save your space? So let's suppose you are given an example, right? Let me give an example. So you are given an example, you are given an array, and in that array you want to search an element. Now the first approach is that you will go and search one by one, right? You will go here, you will iterate through here and here and here. You try to search an element, right? Let's suppose you are searching for 4. In the worst case, you are traversing a big O of n time, right? And in the best case, you are traversing big O of 1 time. This is the best case and this is the worst case, right? So these are the two cases. But this code in itself, whenever you are traversing in a linear fashion, is inefficient, right? And if you're trying to search for an element using different approach, let's suppose you are using a binary search and then you are trying to search an element, obviously your time complexity will reduce. The best case will again remain big O of 1, but it will reduce to big O of log n. Now there are certain parameters, or depending on these parameters, you can define the best, worst and average case of a given problem. So now there are different types of algorithmic analysis, that those are best case, average case and worst case. Okay, so the best case is obviously when you are searching for an element in an array of, let's suppose, 100 size, right, or 1000 size. The best case is that the first element that you look, if you're talking about what, linear search, okay, best case scenario is that the element that you're trying to search is the first element, right? Done. This is your best case and it requires constant amount of time. Now, if you talk about average case, it will be somewhere around the middle, right? About 1000 divided by 2, or you can say big O of n divided by 2. Since we are neglecting, we do not take care of these constant terms, or we can negotiate, or we can neglect these constant terms, because as soon as our input is increased, right? Let's suppose right now we are talking about 1,000 elements. we are talking about 10 billion elements. At that time, dividing by 2 still is same. Okay, not same, but it can be ignored, because as soon as we are increasing our n, let's suppose to 10 crore or more than 10 billion, okay, 100 billion is the input size, right? At that time, dividing by 2 still it is greater than what we can do if we have something around log n, okay? So obviously the average case is still big O of n. Now when you talk about worst case, the element is found at the end, or it is not even found in the array. You are traversing each and every element in the array and still you were not able to find the element. So this is the worst case, okay? Now the worst case is always taken into consideration because this is the maximum resource that you require, okay? When you talk about time complexity or space complexity, right? So time and space, right? So you always talk about worst case scenario, right? And you always deduce your time and space complexities based on worst case. It is computed because the analysis as it dictates the maximum resource requirements. So worst case helps us to find what are the maximum resources that this is going to take, okay? So we keep track of those things and we allocate resources in such manner. So we always talk about worst case. Now let me give you an example of linear and binary search. So in linear search, right, we always talk about it, and in binary search, the space complexity of both these algorithms is constant in worst case, right? And if you talk about the best cases of linear and binary search, it is again constant, right? And it is again same, okay? Now when you talk about big O of n, now when you talk about the worst case scenario, right? And this is what helps us to differentiate between binary and linear search, the worst case scenario. The worst case scenario for linear search is big O of n, wherein for binary search it is big O of log. Now let's suppose there are 8 inputs, you're going to traverse 8 times in this linear search. But if you have this log 8, the base 2 value, it reduces, or you can reduce it to 3 into log 2 to the base 2, which is 3 times. So in this you are only iterating 3 times. In this you are iterating 8 times. Now as you can see, that input is very low or very less. That means there are only 8 elements. As soon as our input, our n, or the number of elements in the array grows, this size of these iterations become substantial, and that is for the same reason we always talk about worst case scenario. Okay, now let's talk about time complexity. It determines the total number of unit operations to be undertaken to solve a particular problem, right? Let's suppose, let me take an example of number of iterations, like, so if you are able to search an element in a single unit of operation, then it is termed to be a constant operation. And if you're doing the same for number of inputs, let's suppose there are n elements and you're traversing to find a particular element, you're traversing n times, so it's termed to be a big O of n. So to solve a particular problem, you determine the number of unit operations. Now, unit operation is an operation that is independent and it can be broken down into simpler operations. It is independent of architecture. It is computed on the basis of algorithm itself. You have an algorithm in place, and based on that, you compute the time complexity of each and every step, right? If there is a loop, what will happen? If there is a condition, what will happen? If there is a while loop, what will happen? It's high priority critical in optimal algorithm selection. Now, depending on this time complexity, you can determine whether you want to go with a particular algorithm or not. Because let's suppose you're trying to search an algorithm, right? You can have 2 options, right? You can use a binary search or you can use a linear search. Now, depending upon the time complexity, binary search works much more faster as compared to linear search. It works in order and it works in department. So time complexity plays a major role, and there is always a trade-off between the time and space. And in this session, we will be covering both of these things. Okay. So now Let's take an example and let's try to determine the time complexity of that particular example. Now let's suppose you are given a for loop, and in that for loop you are iterating from 0 to n, right? Where I is less than n, and then you're doing the plus plus. Now you're doing some work in it, okay? Now since you're traversing from 0 to n, now this is a scenario wherein this will be operated or this will work. The number of unit operations that are present in this for loop is bigger of n. Now similarly there is another for loop in the same program which is operating from 0 to n, okay? And then the same thing, there's a nested for loop in it, and therein what you are doing, you are traversing from 0 to what? Let's suppose this is traversed, n is 8, right? N is equal to 8, and in this for loop you are traversing 8 times, and in this while loop you are traversing 3 times, right? Let's suppose you are multiplying every time by 2, okay? So now in this for loop, the nested for loop, the time complexity of the same is n log n. Now why it is n log n? Because if you observe carefully, number of operations that I told you is 8. So outer loop is working 8 times and the inner loop is working log 2 to the base 8, that is 3 times. So now what is the scenario? What will be the total time complexity? It will be big O of n plus big O of n log n. Okay, this will be the time complexity. Now what is happening over here? This is a scenario wherein what is happening? It is happening m into n. That means you are multiplying big O of n, that is the nest for the nested one, okay, into big O of log n. So you are multiplying it. Whenever you have a situation wherein you have a for loop inside a for loop, therein you will multiply the time complexities. Now you have a for loop outside and then you have this nested for loop. For this nested for loop you have n into log n, right? And for this you have what? Big O of n. Now this is a scenario wherein what happens? M plus n, and in this you will always take into the consideration the maximum number of resources that are there, so that one for loop will take. So in this you are taking only n resources, or this is the time complexity of this is n, and in this you are taking n log n. So obviously this is greater, right? So you always say that the time complexity of that particular problem will be n log n, because you are neglecting these smaller terms. As soon as our input is increased, these terms will be neglected and they will not be that much significant while you are allocating resources. Now what about the space complexity? It determines the total space to be allocated in order to solve a particular problem. Now whenever you are using any extra space in the algorithm while you are implementing it, that is termed to be as space complexity. It can be in the form of arrays, that extra array that you have used to solve a problem, or an extra linked list that you have used to solve a problem, or a stack or a queue, right? It involves memory of the computer, right? You are involving memory, right? You're taking something extra, right? To solve a particular problem. Let's talk about merge sort. Therein you take extra memory, and in worst case you can take big O of n extra memory. That means the number of elements that are present in the array, you're taking the same array as an auxiliary memory, that extra memory, right? It's low priority critical in optimal algorithm selection. When we talk about space complexity, we try to avoid any extra space. We try to solve it with minimal space, right? So that we don't use any of these auxiliary memories. Okay, now let me take an example of a merge sort, wherein in that merge sort, every time you create a left array for the left side and the right side, every time you create these sub-arrays and then you calculate, and then you divide them into further and further unless there is no possible division, and then you start merging them. So again, this is a condition, or this is a scenario wherein you are using extra memory of big O of n. Now if you talk about simpler examples, let's suppose you are trying to change the positions of even and odd numbers, right? So let's suppose you have these indexes, right, in the array, and you have some values. Let's suppose 10, 20, 15, 20, 15, and 10. Let's suppose these are the values, right? Now you want to use, or you want to find out the frequency of these numbers. So you will be using another array, and in that array what you will be doing, let's suppose you are picking up this 10 and you are storing it in this. Now you'll be checking, okay, if this is already present, pick up the counter and keep track of how many times this 10 occurred. Now this will work only for when you are trying to search 10 throughout the array. I'm taking a naive example, right? So I'm taking this example and I'm trying to search 10 and I'm trying to calculate how many times it has occurred. So you place a 10 in this array, and then what you are doing, you will just iterate through the array and then keep a track of this, how many times this has occurred, and keep incrementing the counter, right? So now you're using an extra space, right? Now even if this example is not understood, let me take another example. Let's suppose you're using a recursion, right? You might be thinking, okay, internally you are not using any extra space, but what happens in recursion? Every time the recursion is there, that means function calling itself, an activation record is created and a stack is used internally, wherein your main function will be there and the number of function calls, right? The function calling itself, function calling itself, function calling itself we will be pushing it on the stack, and once you have returned, then we will be popping it out, right? So internally you are using an extra memory, and it depends on from program to program. Are you using big O of n, or are you using log n space? But internally recursion uses extra memory. So an auxiliary memory, or you can say that extra memory, is used while you are using recursion. So that is why we try to avoid recursive problems, and we try to solve our problems using iteration. So which is obviously that we are not using any auxiliary memory, although it is internally, but still recursion uses extra memory, and that thing is taken into consideration. Now you might be thinking, okay, now should we use, or should we save space, or should we use less time? Should we go for time efficient algorithm or space efficient algorithm? Now there is always a trade-off between space and time. So in some problems they might ask you to save or to write an efficient algorithm, keeping the time into consideration, that you don't have to use extra time. But in some they might say, okay, you can use extra space, but time should be efficient. Or in some cases they say use as much time as you want, but space should be less. So that is also there. So there's always a trade-off between both.